A topological space is a foundational mathematical structure that allows us to define concepts like closeness and continuity. Without it, a collection of points is just chaotic data. With it, we have geometry. But in general topology, we rarely define these spaces by explicitly listing every single open set. Because a space can contain an infinite number of points, listing its open sets one by one is impossible. Instead, mathematicians rely on underlying logical rules. We use strict axioms to systematically generate valid topologies from smaller, more manageable collections of sets. There are three primary ways to do this. The first method builds a topology from a sequence of elements, known as the order topology. The second method creates new spaces by multiplying existing topological spaces together. This is the product topology. The third method defines a smaller space by extracting it from a larger parent space, which we call the subspace topology. Individually, these generation rules are perfectly logical, but when they are combined on the same set of points, their governing axioms can directly conflict. The topology a subset inherits from an ordered parent space is not always the same as the topology generated by its own internal order. To see how these systems break down and how mathematics resolves the paradox, we have to look at exactly how these rules are built. The baseline requirement for the order topology is a simple order relation. This means for any two distinct elements in a set, one must strictly precede the other. Looking at this text, we define the basis for the order topology using four specific types of intervals. A basis is just a collection of sets whose unions can form every possible open set in the topology. Notice the inclusion of half-open intervals. If the overall set has an absolute minimum, represented here by A0, or an absolute maximum, B0, any open set containing those extreme endpoints must include them as a closed boundary. From bounded intervals, we can expand our view to open rays, which extend from a point infinitely in one direction. This section defines four distinct rays extending from a single element, A. The first two open rays serve as a subbasis for the order topology. This means by simply taking finite intersections of these infinite open rays, we can reconstruct the basic bounded intervals we just established. But applying order topologies can yield counterintuitive results. Take a set defined as the elements 1 and 2, multiplied by the positive integers, using a dictionary order. In this sequence, most individual points qualify as open sets, but the element B1 is an exception. Because of how the order is structured, any basis element containing B1 is forced to overlap and contain points from the preceding A sequence. The order topology perfectly maps the continuous geometry of a sequence. But as the B1 example shows, it relies strictly on structural logic, rather than visual intuition, to dictate what is open. If we move to two dimensions, like the Cartesian plane, we need a method to rigorously define the topology of the resulting coordinate space. This is achieved through the product topology. It defines how topological spaces X and Y combine. This diagram outlines the logic. If U is an open subset on the x-axis, and V is an open subset on the y-axis, their product forms a basic open rectangle. When two distinct basis rectangles overlap, their intersection produces a new, smaller basis element within the product space. We can also generate this topology using a subbasis, defined by mathematical functions. We define two projection functions, pi1 and pi2. Their only job is to map points located within the 2D product space back to their original 1D axes. Looking at figure 15.2, taking the inverse projection of an open set U on the x-axis creates a vertical strip that extends infinitely. The inverse projection of an open set V on the y-axis creates an infinite horizontal strip. By finding the exact region where these two infinite subbasis strips intersect, we perfectly recreate the original basic open rectangle, U cross V. Multidimensional topological spaces are precisely constructed by intersecting these independent lower-dimensional shadows. The final generative method does not combine spaces, but extracts a subset Y from an already existing topological space X. This equation states the rule for the subspace topology. The open sets of Y consist of all intersections of the open sets of X with the subset Y. To identify the geometry of the subset, you must intersect it with every open set that belongs to the parent space. This forced intersection rule produces a condition known as relative openness. Suppose the subset Y is the closed interval from 0 to 1 on the real number line X. If we take an open interval U in the parent space, spanning from negative 0.5 to positive 0.5, and drop it down to intersect Y, the overlap produces the half-open interval from 0 to 0.5. Under the strict intersection rule of the subspace topology, this slice is perfectly legal as an open set within Y. Because it contains the hard boundary of 0, it is closed in the context of the parent space, but restricted entirely to the subspace, it is completely open. Subspaces are submissive to the rules of their parents. They inherit their geometry strictly through intersection, meaning the definition of an open set depends entirely on which boundary you are observing it from. We now have two competing rules: sequence generation and subspace inheritance. The conflict arises when we have an ordered set X and an ordered subset Y residing inside it. There are two valid paths to determine the topology of Y. In path A, Y blindly inherits its open sets by intersecting with the parent space X. In path B, we ignore the parent space completely. We observe the order relation of the elements strictly within Y and generate an order topology purely from the inside out. Do these two entirely different sets of axioms produce the exact same geometric space? The answer is no. According to Theorem 16.4, these two methods only generate the exact same topology if the subset Y is convex. In topology, convex requires that if 2 points exist in subset Y, every single point located between them in the parent space must also belong to Y. The subset cannot have any gaps. Figure 16.1 proves exactly why a lack of convexity causes the axioms to clash. In the left diagram, an open ray from the parent space intersects with a non-convex subset Y. Because it follows the inheritance rule, the intersection forcefully defines a specific open set within the subspace. In the right diagram, we attempt to construct an open ray using only the ordered elements inside Y. But because Y has a physical gap in its structure, the internal ray generation skips over the missing elements. It fails to recreate the exact shape defined by the intersection rule. The math holds a strict verdict. If Y is not convex, its inherited subspace topology will contain open sets that its own internal order topology is simply incapable of generating. This is a persistent trap in higher mathematics. Assuming that logical frameworks will naturally align without strictly verifying the underlying conditions leads to structural breakdown. A topological space is deeply sensitive to the precise axioms used to build it. Identifying where generative rules conflict and writing theorems to reconcile them is the mechanism mathematics uses to ensure its own rigorous survival.